Okay, hi everyone. We are back. I'll just do a quick audio checkup. Yes, but I guess you won't be able to. Let me just check.
That it wraps and keeps track of.
Yeah,
And
you will be able to hear the Windows voice also, the video's voice also. Okay, so in last part 2, the whole essence of that session was to understand slope of a function, that what does it actually means when someone says that that find the slope of a function. Okay, we are still not able to understand 100% that what does it actually means, but yeah, we have drilled down, we are drilled down a good amount of chat with this. Okay, and the basic drilling, and we have reached, by drilling this much down, we have reached at a point that where it demands the understanding for quadratic equations and all of that, polynomials basically. So so if I say that functions can be represented as polynomials, degree of 1, degree of 2, degree of 3, up to degree of n. So if there is a straight line, then it is represented as y equals to mx plus b. Everyone knows it. Why? Because there are no turns in it. Turns, what do you mean by turns? So turn is a place. Let's consider it as a place. Turn is a place where a change happens. Let's say, let's say, in this graph, if I'll just zoom in, yeah, zoom in. If I'll just zoom in this, then it is represented as this. Okay. So this point is known as one turn. Why? Because some change is happening here. See, here the function is increasing. Okay. Here the function is remaining constant. Means there is no change. And here the function is decreasing. Means there is an increase, then there is no change, and there is a decrease. So this whole thing is known as a turn. Now, straight lines don't have any turns, right? It will be, it will be, you know, it will be a constant increase in the function, okay, or constant decrease. So, but as soon as there is some tweaking, let's say this, or uh, let's say this, okay, let's say this. So this is not a straight line. It has become a curve. It's a curve. It's not a straight line. It's a curve now. And curves does have one turning point. Okay, one minimum. Uh, if a line has one turning point, then it's a curve. It's not a line. Means that the graph was going. Let's say if I'll zoom in, okay, it's increasing in this manner. Okay, it's increasing now, and at this point it has reached some sort of constant. There is not much change. But after at this point, there's an increase, you know, there's a rapid increase in change and it has got much steeper. So we can consider this as a curve. We can consider this as a turn, right? And usually this sort of equations are ax square plus bx plus c. Why? I don't know. But this is y equals to mx plus b. Okay. Now there is an another term called this. Okay. This is 1, this is 2, yeah, this is 3. This is represented by, again, there are 3 turns here, that is 1, 2, and 3, right? You can also count them as peaks and valleys. The number of peaks, the total number of peaks and valleys are equal to turns. So this is one peak, this is second peak, and this is valley. So two peaks plus one valley equals to 3 turns, right? And these type of functions are represented by ax cube plus bx square plus cx plus d, and so on. It is, it get continues, up to nth degree polynomial, right? But I don't know why this lines are represented by this, why line is represented by this mx plus b, why curves are represented by ax squared plus bx plus c, and all of that. Okay. Now, so the question I had is, why this equation, why this equation has three peaks, three turns. Why this equation has one turn? Why? So it turns out, sorry, so it comes out that these three turns is because this equation has three roots. Similarly, this has two roots. Sorry, one root. But now what are roots, right? Roots are, let's say, I have a quadratic equation of 3x square. I'm just randomly writing it down, right? 3x square minus x plus 4 equals to 0. 1, 3 minus 1. No, I need to write something, no? 2. No. Right, let me just rewrite it down. 3x square, 3x square minus x plus 3 equals to 0. So the roots of this equation is x equals to 1. No, x equals to 0. X equals to 0 can be the root, obviously. No, x equals to 0. Should I, if I go for this? Yeah, go for this, and if I x equals to minus 1. I don't know. Yeah. In a way, I need to, yeah, इसमें दिया होगा ना इसका कोई equation. Okay, yeah, let's take this. Minus 5x squared plus 20x plus 2. And the roots are here. Point 10, 4.10. So in a way, I'm not able to understand this properly. So let's still research about this. Let's understand this properly. Okay, so I have two questions in my mind right now. Uh, why number of turns equals to number of roots? Okay. Second thing that I wanted to understand more is why straight line, why these lines are represented by this. By polynomials. So first of all, let's go through this. I'll start the timer. Okay. It will be a 1 hour session only. But I know it's getting deeper. Let me just write this that now we have the questions raised are uh, why, how to map a function. Nah. Why mapping why a function is always represented as polynomial. Why a function is always represented as polynomial. Okay. Uh, this is first part. Okay. Why a function is always represented and why the roots of a polynomial polynomial represents the number of peaks or peak or valleys of a curve. ये क्वेश्चन है ठीक है so here it has given me real world analysis of root. Should I go on YouTube and find something? Uh, quadratic equations visualized. But where is the formula?
The visualization of a quadratic equation. I have a similar one here, y equals to the second power. The exponent is 2 for the variable x. This is a function, a quadratic function. We are going to explore how that equation looks like. and we can make connection with the one from Galileo. See how it looks like. This is the representation of a quadratic equation. Is that parabola. And when I said take this chance or take this opportunity is because I want you as a teacher or a student to explore different areas of the mathematics and make connections. Algebra, history, and now analytic geometry, which is the visualization of one equation in one graph. This is the evolution of the history of mathematics. Very interesting.
Hey developers, join us for the biggest AI competition with over $10,000 in cash prizes. Yep, that's right.
As early as 2000 BC, we already have This is one of the most famous formulas in all of human history. It's the quadratic formula. It describes the zeros of any quadratic function. Most people learn this formula by memory, but very few actually understand why it works, where it comes from, and can appreciate the beauty behind its development. Just as a quick recap, the quadratic formula describes the points shown here on the graph, which are basically the zeros of any quadratic function. In other words, the points where the function, the line in red, intersects the line x equals 0. In more algebraic terms, the quadratic formula is therefore the solution to the following equation shown on the screen, with the left-hand side being the formula of any quadratic and the right-hand side being just 0. Interestingly enough, the quadratic formula that we know and love is actually not that old. As early as 2000 BC, we already have records of people working on quadratic problems in ancient Babylon in a far more geometric way than in the way that it is treated today. Then later on in 300 BC, the ancient Greeks were already dealing with special cases of the quadratic formula with explicit solutions. This continued in 600 to 900 AD, with Persian and Indian mathematicians dealing with more special cases of the quadratic formula with explicit solutions again. But it really wasn't until 1637 AD when we got the quadratic equation that we know and love today with all of its beautiful notation, when we got all the solutions to any case of the quadratic formula, not just the special cases. So we can see that such an elementary formula as the quadratic formula is not even 400 years old yet, which is quite amazing in my opinion. But enough about its history, let's actually try and solve the quadratic formula now and derive where it comes from. So we start with the equation here on the screen. And one thing we can do is just try and solve for x to get the quadratic formula. To do this, one place where you can start is just by noticing that if a is not 0, we can divide everything by a. Now, we want to isolate x, but we have terms here with x squared and x. So one trick we can use is just to complete the square. I'm not going to explain in detail what this entails, but just notice that the following formula here will give us a nice identity to work with. The formula on the bottom is very similar to the formula on top, but on the left-hand side of the formula on the bottom, we have x contained in these parentheses, which is very useful if we want to isolate x. In fact, if we just rearrange the formula on the bottom a little bit, we can make it look a lot like the formula on top. And now that we have them so similar, we can actually just substitute the bottom one into the top one to get a very nice expression for x. Now we basically have x containing these parentheses, and all that remains is just to algebraically manipulate this and simplify to get x on one side, which shouldn't be so difficult. First, we move the terms on the other side. Now we can simplify this fraction a little bit and make a common denominator. Already here we can also tell we're getting close because we have b squared minus 4ac already on the numerator of the right-hand side of the equation. But what we really fail to appreciate as well is how beautiful and how useful this quadratic formula is. Because notice that if we just rewrite this formula in terms of its form as shown before, we have now that this basically tells us there's a sort of symmetry to the solutions to the roots of the quadratic, in that they're both symmetrical across the line of symmetry. So if you take the point minus b over 2a, you either add the square root of b squared minus 4ac over 4a squared, or you subtract it, but whichever one of those.
Oh, bro.
Underneath this heading, I will move on as why we don't let it.
For example, let's say later in life you find yourself wanting to understand quadratic functions. And so here we're going to talk about the simpler version of the quadratic formula, which is really just refactoring the original thing. But I hope you see it's much easier to actually solve a random quadratic that's thrown at you if you're going by the method that I want to show you right here. So what's the task? Anytime you have some function that looks like ax squared plus bx plus c, okay, for any numbers a, b, and c. So maybe that's something like 3x squared minus 4x plus 5. And you want to know when that equals 0, what are the two roots? Now, this is actually equivalent to rescaling everything, and I think it's a good common pattern to rescaling, where I'm going to divide everything by a. So I just want that first coefficient to be a 1, because that's way easier to work with. So I'm going to call that x squared plus b prime x plus c prime, where b prime and c prime are just the rescaled versions there. And this is a different function. It is a different quadratic function, but the roots are going to be the same. And one way that you might see this is if you just graph them. So let's go over and pull up our best friend of Desmos, right? So let's say I have some kind of parabola. In this case, I've written it so that one of the roots is going to be 2 and the other is 4. And then g of x here is just the scaled version of, the expanded version of that. It's exactly the same graph. But let's say I wanted to scale that up and down, right? So I might take this and then I will multiply it by some kind of constant. What do you guys want to call that constant? See, this is the thing. If I had the question framework working right now, I could just ask you, what do you want the constant to be? And we would see the statistics come up with what people had. But instead, maybe I'll throw in a slider. And as I change that, the function changes. It is a different function, but the roots are still 2 and 4. Okay? So solving for this rescaled version of the quadratic is the same. And that should kind of make sense, because s times 0 is always going to be 0. So it doesn't matter how much we scale it. So going back to what we're working with here, the reason that I think it's much nicer to make sure that that leading coefficient is a 1 is because if we're thinking of our quadratic in terms of its roots, and I say, okay, you know, it's going to intersect the x-axis at r and s, or maybe it does, maybe it doesn't, but let's just write one that does, like this. Another way that I could express that particular quadratic is as x at r and s, or maybe it does, maybe it doesn't, but let's just write one that does, like this. Another way that I could express that particular quadratic is as x minus r times x minus s. Because if I plug in r, it's clear that we're going to get 0. And if I plug in s, again, this term will also cancel out to 0. So if I expand this, whatever r and s are, they're the unknowns, I should get the same thing as what we have up here. And this is generally useful. This is not just for the quadratic formula, but a very good relationship to have with polynomials is to know how the roots correspond to the coefficients, especially in a circumstance where that leading coefficient is 1, and the whole polynomial's been kind of normalized in that way. And in this case, if you just expand it out, what we'll get is x squared minus r plus s times x, because we have this minus r times x and then x times minus s. And then the constant term will be negative r times negative s, so that becomes a positive r times s. Okay? So what does this tell us? This tells us the first two of the 3 key facts that are needed to be able to solve any quadratic without really needing to memorize all that much. So the first key fact is that this b value, I'll call it b prime just to remind ourselves that it's after you've scaled things down, is the same as the negative sum of the two roots. Okay? And then similarly, c prime is going to be the product of those two roots, which is kind of cool, because what we have right here is, you know, it's a system that feels like it should have a solution. We have 2 equations and 2 unknowns. which is the only thing we don't know left. You can rederive it on the fly. There's not too much memorization needed. In this context, that we're now is where the input lives, where x lives. If you were going to grind, okay, so that's fun. In this case, the square root is a negative that we could express that product of roots as a difference of squares. We have m plus or minus. Like, the plurality of you are definitionally correct.
We all know these three methods of solving a quadratic equation. The first one is by using the direct formula, in which we have us whose and this value. So roots of this equation is
Today we're going to take the mystery out of quadratic equations. So the lecture today says understanding quadratic equations. So what are quadratic equations? Well, what they are is a relationship between two variables, typically y and x, and it typically will look something like this. Y equals ax squared plus bx plus c. Now that's the standard form, as we call it. A, b, and c are simple constants, any sort of numbers. X is the independent variable, and then y is the dependent variable. So as an example, let's write an equation such as y equals, let's say, x squared minus 6x plus 5. Okay, in this case, a would equal 1. That's the coefficient from the x squared term. B is equal to minus 6, and c is equal to 5. All right. Now, one of the things we want to be able to do with one of these quadratic equations is learn how to graph it. Another one is learn how to find the roots. But before we get into all that, let's kind of get a general feeling of what a quadratic equation is. It's, again, a relation between x and y, so we should be able to graph it on an xy plane. So there's our y-axis, there's our x-axis. And typically, a quadratic equation will be graphed. Either it will look like this, or it will look like that. And the way you can tell if it's going to open upward or open downward, as we call it, is if the number in front of the x squared term is positive, it looks like this. So that's a plus a. And if the number in front of the x squared term is negative, then it looks like this. So think of it as a minus a. All right, that helps us a little bit. Now also realize that if you graph these, that this parabola, as we call them, these graphs for quadratic equations called parabolas, and it could potentially, if we were to graph it, it could end up looking like this, or it can end up looking like this, or it can end up looking like that, or maybe it looks like this. And notice that in some cases, the parabola will cross the x-axis. Like this particular parabola will cross it in two places, this particular parabola will cross it in two places, and these two parabolas do not cross the x-axis at all. The places where one of these parabolas, which is a graphical representation of a quadratic equation like this, where the parabola crosses the x-axis, those are called the roots of the quadratic equation. So we call these roots. And here again, these would be considered the roots of the quadratic equation. Notice that these two do not have roots. So sometimes when they ask you to solve a quadratic equation, they're basically asking you to find the roots of the parabola. And of course, if the parabola does not cross the x-axis, like again, this is here the x-axis, this here is the y-axis, like in this case or in this case, then there's no solution, there are no roots to the quadratic equation. All right. So to help us figure out what it actually is and how to graph these quadratic equations, let's go ahead and factor this. This happens to be a factorable equation, so we can write this as y is equal to the product of two binomials. We write the x and the x. Since there's a negative here and a positive there, that means one must be plus and one must be negative. Or no, in that case, I'm sorry, actually they both must be negative. Negative because the only way you can get a positive number there is either that you have two positive numbers here or two negative numbers, and since this is negative, you have to have two negative numbers. So now we're looking for two numbers. When you multiply them, you get a 5. When you add them, you get a 6. So it looks like a 5 and a 1, because if I multiply x times a negative 1 and multiply negative 5 times an x and add them together, I get a negative 6x, my middle term. All right. Now, if we want to solve a quadratic equation, find the roots, realize that the roots are the points that lie on the x-axis. That means at that location, the y value is equal to 0. So any point on the x-axis, my y value is 0, which means if I'm going to find the roots, I'm going to set my y equal to 0. If I do that, this equation now becomes 0 is equal to x minus 5 times x minus 1. And if I solve this for x, then I will find the points where the equation crosses the x-axis. All right, now if I have two quantities multiplied together and the solution is 0, that means either one or the other must be 0, because the only way you can multiply two things together and get 0 is if either x minus 5 equals 0 or the x minus 1 equals 0. And of course, if x minus 5 equals 0, then x must equal 5, or if x minus 1 equals 0, then x must equal 1. And those are the locations in this particular example where the parabola will cross the x-axis. So if I'm going to graph what I have here, my example, if I'm going to graph this example on my xy axis here, I know that one of the roots, or one of the points where the graph will cross the x-axis, x equals 5. 1, 2, 3, 4, 5, so right there. And the other place where it crosses the x-axis will be at x equals 1, which is right here. And those are considered the two roots of my quadratic equation. All right, now there's another thing about a quadratic equation that's very important. It's called the axis of symmetry. If I find the midway points between those two numbers, so this is 1, 2, 3, 4, 5, and so the midway between 1 and 5 is the number 3. If I now draw a dashed line, a vertical line, through the point x equals 3 on the x-axis, that is now called the axis of symmetry. And again, if you look at my examples over here, if you draw a line halfway between here and halfway between right there, and right in the middle there, right in the middle there, right in the middle there, and right in the middle there, notice those lines, those dashed lines, are the exact line that divides the parabola in two equal parts. Therefore, that's called the axis of symmetry. Now, notice that the number from the x squared term is positive. It's positive 1. That means the parabola opens upward. That means I'm going to have a parabola that looks kind of like this. To find a few more details, if I now plug into my equation the value of x, where the axis of symmetry goes right through, in this case, the number 3. So I'm going to solve for my equation when x equals 3. That's again the point where the axis of symmetry goes right through. Let's see what I get. So I'm taking my equation, and instead of x, I'm going to write a 3. So I get a 3 squared minus 6 times 3 plus 5. So notice I took my original example. Instead of an x, I write a 3. Instead of this x, I write a 3. And if I work that out, I get 9 minus 6 times 3 is 18 plus 5. And so that's plus 14 minus 18. That's equal to minus 4. So that means when x equals 3, my y will be negative 4. So 1, 2, 3, 4. That's negative 4 right here. So x equals 3, y equals negative 3. That is the bottom or top point of my parabola. So if my parabola opens upward, the lowest point of my parabola is this point right there. If my parabola opens downward, then my lowest, or in this case my highest point right there, will be that point right there. So in this case, since a is a positive number, my parabola opens upward, so this will be my lowest point on my parabola, also known as the vertex.
Welcome to How to Start a Startup. In this course, I'll share with you the exact steps I took to build my own business, Contact Out.
So that's the vertex of my parabola. Now there's one more special point about the parabola. Sometimes the parabola will cross the y-axis, like over here. In this case, it doesn't look like it, but if it goes on, if you keep going long enough, again, eventually you will cross the y-axis. Right here, this parabola crosses the y-axis over here. And if this parabola goes on long enough, eventually you can see way down here somewhere, the parabola will also cross the y-axis. How do we find that point? Well, remember, anytime you cross the y-axis, that means that the x value must equal 0. So to find that particular point, we take our initial equation again and plug in 0 for x to see where the equation or where the parabola crosses the y-axis. So I'm going to solve for y when x is equal to 0. Again, I take my equation right there, plug in a 0 for every x that I find. So I get 0 squared minus 6 times 0 plus 5, or y when x equals 0 is equal to 5. So going to my example here, my graph, when x equals 0, my y value should be 5. So it's 1, 2, 3, 4, and 5. And so my parabola must cross that point as well. Now notice I have 4 points. I know my equation can be graphed like a parabola. Here's my lowest point or the vertex. There's my 2 roots. There's the point where the parabola crosses the y-axis. If I now carefully connect all those dots with a free hand like that, I have now drawn a graphical representation of my example right here, my quadratic equation, and you can see how that looks like a nice parabola. So that's what a parabola is. That's what a quadratic equation represents. And if you want to look at the points very carefully again, notice you have the lowest point on your parabola called the vertex. You have the 2 points where the parabola will cross the x-axis. Those are also known as the roots. So that's a root. That's a root right there. Also notice that most parabolas will cross the y-axis, and when they do, that's the point you can find. You can find that point by plugging in 0 for x in your equation. And then, of course, the axis of symmetry runs right midpoint between the 2 roots, or also goes right through the vertex. So there you get a pretty good feel for what a parabola is and for what a quadratic equation is. All right, now we're going to show you some examples of actually how to solve these quadratic equations and how.
Bro, crazy video, yeah, crazy. Why a function is always represented, why the roots are represented, number of peaks of, so yeah, so we can, oh, okay, so I do get to know that, let's say if this is a parabola and the roots, finding roots of a parabola means finding the value of x where the value of y is 0. Means in this ax square plus bx plus c equals to 0, that this is y of x is dependent of x square. Okay, y. So when y, it is telling us to find the value of, it is telling us to find the value of x points on the graph where the value of y equals to 0. Okay, so that we understood. Now, what does this mean? Uh, uh, Imagine you throw a ball into air and its height is modeled by quadratic equation minus 5t square plus 20t plus. So minus 5 is, then it will be like this. Okay. Acha. So minus 5 is there, so it will be okay. So you threw a ball as a in that manner, right? At time t. So this will be uh, time t and this will be h of t. Okay. So h of t, it is similar to y of x. This is a relationship between two variables, x squared plus vx plus c. ठीक है, and it is minus 5 t square plus 5t 20t 20t plus 2, right? So actually, okay, so finding the roots of this, let's say I am able to find the roots of this, right? Roots of this equation means, अगर मैंने if I was if I'm sorry if I'm able to find the roots of this equation, then what does it actually mean? So I will be able to find the time at which the ball will reach to the ground. Are you getting me? Let's say, bro, this is beauty, yaar. This is beauty. Let's say, you are standing here, right? You are standing here. Okay, you are a point-like structure in this universe. Obviously, you are a point-like structure, and you threw a ball above this. Okay, and it has been traveling like this. Okay, this is time t seconds. Okay, at time t equals to 1, the ball was, you know, time t equals to 0, it was in your hand. Time t equals to 1, it uh, went this much in the air, that is height at 1. Okay, at t equals to 5 seconds, it went this much higher, height at 5 seconds. Okay, so now I want to find when this, okay, now I want to find when will this ball will touch to the ground. Means touch to the ground means uh its height is 0. Okay, height is 0, right? Here height of 5 means this is 50 meters, this is 10 meters. Okay, so at h of 5 means height at 5 seconds was 50 meters. That is, the ball reached the ball after 5 seconds reached to the height of 50 meters. Okay, what does this mean? H of 1, it means that after 1 second the ball reached the height of 10 meters, right? Now, now with this, I will have a question in my mind that at what time the ball will hit to the ground. Okay, so in a way we are telling to find the time where the height is equal to 0 meter. right? So what we will be going to do is we'll take this equation h. What is this equation? H of t equals to minus phi t square plus 20t plus 2, right? And we will be finding the roots of this. Wait a minute, guys, I'll be back. Yeah. So what we are actually finding is we are finding the value, we are finding the time. So if I solve this quadratic equation, that is minus phi t square plus 20t plus 2. I actually forgot this, but what we can represent is minus phi t square. 5 was the 20. 5 to the 10. No, no, I don't know how to solve this. So I don't remember to solve this, but now I get to know that here by finding t, we will be able to find the time at which the height of the ball is 0. That is I understand. The concept is clear now. Similarly, imagine a parabolic bridge. Okay, parabolic bridge. This is also a bridge of minus x square. So it will be of a U shape. The quadratic for its shape is minus x square plus 6x plus 8. X equals to distance another one, y equals to height of the arc. Yeah. So the roots are at bed. हाँ तो it the end points कब में होंगे? Yeah, got it. The two end points minus x square plus 6x plus 8. 6x no. हाँ तो this is we can solve no. X square minus x square plus 6x plus 8. We can solve this by minus x square plus 4x plus 2x plus 8. That is x equals to minus x plus 4 plus 4 to the 8. Yeah, but here, no, no, no. Here, 4x plus 2x. No, here we can just 2 plus x plus 4. Yeah, take us minus x. 8, 4 to the 8. I don't know, man. I'm not able to solve this. But I get to know the concept behind this. See, what this is telling is practical implementation here is let's say you have a bridge of this shape, right? You have this shape of a bridge ठीक है, that is y equals to minus x square plus 6, where y equals to height of the arc. Okay, I'll draw the origin. Okay, the graph is like this. Okay, so the real world scenario here is that someone gives you someone comes up and tells you that I want to make a bridge. I want to make a bridge that has this function, where where the height is height of the arc, or the depression, in this case the depression in the arc, right? It's because it is going down, where the height of the this middle point axis is somewhere y of x. Okay, and then he comes and tells you that to calculate the points at which the bridge will start and end. Okay, so there you have to calculate the roots of this quadratic equation, and by doing so you are indirectly calculating the value of x, the value of x, where value of y equals to x equals y of x equals to 0. It is at this point. This is the y-axis, right? This is 0. So at which values of x the value of y of x is 0. That is actually you are calculating, right? So yeah, this concept is clear. Okay, what does the roots of quadratic equation mean? So this is understood, this is done, right? The roots of quadratic equation means to find the values of x where the value of y of x equals to 0, right? Why, if a polynomial has two roots, will have two terms? This is a question still. I'll just mark it as right. This is clear. Now the another question I had in my mind was, why, if a polynomial which has two roots will have two peaks? So what it has said here is, let's break this down. Patient. The roots of a derivative of a polynomial are the points where the slope is 0. Hmm. So it is telling to get the derivative of a polynomial. I have not started this. So it is telling me to find the derivative of polynomial and the derivative of this roots. Sorry. It is telling me to find the derivative of this polynomial. Okay. And then finding the roots of this derivative. This corresponds to critical points, turning points where the curve. The roots of the derivative are the points where the slope is 0. There are turning points when the slope, the graph is monetarily flat. At such point, the curve can transition from increasing to decreasing or from decreasing to increasing. For a cubic polynomial, y equals to ax cubed the roots of the where the slope. Why do two roots lead to two turns? As two distant, these roots are the x y where the slope is where the y is 0. Critical between this when the curve changes directions twice. The number of real roots of derivative determine how many times the slope becomes 0, which directly translates to turning points. Two roots, two critical points, two changes. I don't get this. But why we are taking the derivative here? Derivative function represents the slope function at instantaneous slope of a function. Instantaneous slope of a function at every point. मतलब कितना उसमें इंक्रीज और डिक्रीज हुआ है या कांस्टेंट. अच्छा. ओके. Yeah. I got it, bro. Similarly, for this logic, let's say जो कौन सा लॉजिक था हमारा h of t, right? H of height of t equals to minus pi t square plus 20t plus 2. C. For finding these are the points where curve becomes flat for a very momentary time, right? Sorry, slope becomes flat, means there is no increase, no decrease. So here, let's say here, okay, this is a point where there is no notable decrease or increase up till here. We have to find these points, and that is why if I'm taking a derivative on the left side, like finding dh by dt equals to 0, difference in height and upon difference in time, when equals to limit t tends to close to 0, right? तो जब t में बहुत ही कम डिफरेंस है जिसका, तो मुझे डिफरेंशिएशन लेना पड़ेगा with reference to t, so that is okay. खेल हम यहाँ पे the main play here is how we can calculate, how we can bring 0 in this right hand side of equation, so that we can be able to find the roots. Y equals to 0. dy by dx. Y equals to 0. Question here was, and then we can but for the parabola उसमें क्यों नहीं लिया? No. अच्छा, अबे रुको ये. So what he's telling is, let's take this example only. It's working good for us. The ball, let's shoot it from here. Okay, so this will be the first route, obviously, because at this let's say x1, the height of the ball height is at 0, right? It has traveled this much, not x1. Yeah, let's go for t. At t1, the height is at 0. Okay, so it has went upside like this, and it has gone downside, just like this. This is time t2. Okay, so this is the time where the ball will hit to the ground, and the height is 0, right? But what is telling is that if we want to find the maximum height, then we have to maximum height, like at which time this this telling us to find this only, no, vertex only, no, at which point at how many seconds this height will be reached. Okay, how many seconds? So for that we have to take derivatives, because derivatives give us the instantaneous change in slope. Means that at a particular point, if the function is increasing, decreasing, or staying constant. Okay, so this is the time, this will be the time where uh, the for a very small moment of time, the slope will be constant, right? For a very small moment of time, the slope will be constant, means the slope will be 0. H of t, the slope will be 0. That is dh by dt will be 0. Hmm. Means स्लोप एंड हाइट का चक्कर है, because मैक्सिमम हाइट पे जब वो बॉल पहुंची होगी, तब उसका स्लोप 0 हो गया होगा. वाई? बिकॉज एक मूवमेंट के लिए देयर वाज नो इंक्रीज नो डिक्रीज, उसके बाद डिक्रीज होना चालू हुआ होगा, राइट? दैट इज वाई दैट इज वाई ये जो क्वेश्चन था मेरा, हाँ, this question of mine, why a function is always dependent on why the roots of are given number of peaks. Yeah, it is for that moment only. So if I have 2 or 3 peaks or down like this much, then the root at this point, okay, time at this point and time at this point will be the solving will allow us to solve because it is giving us the maximum height, max height and min height, right? Max height means this one where the height was where the instantaneous slope became for a very small moment the slope became 0. That allows us to do that. And this one is also this, right? Okay. And if we are able to find the roots of this, like if we are able to find a time t, then we'll have the roots. Oh, still it's blurry. It's 80 to 90% clear then that y. Oh, wow. Oh, as explained in spotting graph. So also tell me real world analogies. What does roots of quadratic equation? Roots of quadratic equation means it's finding the values of x where the value of y of x equals to 0. That is understood. Why if a polynomial has two roots will have two terms? Yeah, this is also clear. Right? Because what we are doing is it's not a straight line first of all. So whenever uh, whenever there is a curve, okay, so curve has a peak and depression, okay, increasing and decreasing. But for this point, at this point, let's say if we consider every point, let's say the curve is increasing like this and it was like down for this. So if I'll start putting out every point, this is 1 point, this is 2 point, this is 3 point, this is 4 point, this is 5, this up till this. So up till this point and this point will have an increased slope because they are because the slope is increasing. But points like this, this, they won't have any slope. They will have a constant energy. But even if it is for very small movement, but they will have zero slope, right? So we are targeting this slope, okay, and this is the maximum height. Okay, you can always consider that this is the maximum height where the object, for a very small movement, stayed at that place. The ball when I threw up, for a very small moment, it stayed at that place, and that is this point where there was no sudden increase or sudden decrease in the slope, right? So we are finding these points. Let's say I'm finding the time at this point. I'm finding the time at this point, which means I want to find uh okay, if I'll just write in this manner, it will create confusion. What I can do is hmm, hmm. So let's just create this is as um T1, this is as T2, right? And the difference between them is very small. That is delta of T equals to it's very small. It's 0.0001 seconds, which we can say that it is very close to 0. Okay, and when I'll when I grab the height, that is h2, let's say h2 minus h1, it won't have much difference because the slope is 0, right? It won't, it is also 0. So when I do this, it is indirectly I'm telling dh by dt equals to 0. That is, I am, and the equation was like h of t. This is the function. Okay, this is the function of minus. Where does it went? Yeah, minus 5t square plus 20t plus 2. Minus 5t square plus 20t plus 2. So if I'm taking derivative this side, then I'll have to take derivative this side also, right? So if I'll go for like this, dh by dt, if I take derivative with respect to t, then it will be minus 10t plus 20, right? Okay, and the value of dh by dt here is 0. Okay, so if I'll minus 10t plus 20, okay, now if I'll put this here, so then it is called, if I'll just remove, yeah, I can just for FODMAS rule I need to divide by 10. Dividing by 10, so this will give me 0. This is minus t plus 2, right? Clear? Remember minus 10, bro. It should be minus 10. Dividing by minus 10, right? This is this. This will be. This is 0. This is t minus 2. So if I'll add plus 2 at both sides, so I'll get 2, t equals to 2. That is, at t equals to 2 seconds, the slope was 0. Means we don't know, okay, we don't know here, but we don't know if it is maximum or minimum, right? Because slope can be, yeah, this is similar for this only, this also. But if it is minus 5t square, then it should, this is a proper definition, right? So we still, I mean, but how we are going to determine, but at t equals to 2 seconds, we know the slope was 0, but this is, but we are still unclear that whether it was a peak or a valley, right? Are you getting me? Because we still know that at t equals to 2 seconds, But it is possible if we think, because obviously we have thrown the ball towards the sky, so it's a peak only. But this is I need to check. Okay, so at t equals to 2 seconds, the slope was 0. That's where we find. So it has one root. We can say this t equals to 2 as root, right? Means one peak or one valley will have one root, one flat point, where the slope is 0. Similarly, for a graph like this, will have two roots or two flat points where the slope is 0, right? For this is 1, this is 2, this is 3, 4, 5, 6. It has 6 roots. Okay, so let me just ask this in a different way. So for a function having 6 roots, it means that the total number of turns peaks and valleys will be 6. No. The roots, I thought it will be 6 only, so I have not understood this properly not till still. Roots are the point where the function intersects at x-axis. A polynomial of degree n can have up to n roots. Okay. These roots are solution to the equation of f of x equal to 0. Okay. Turns are the points where the curve changes direction. Occur where the slope of f of the maximum number of turning points for polynomial of degree n is n minus n. Acha. Why? Okay. The number of okay, that is correct. But the number of roots is determined by the behavior when related to x, while the x and how the curve changes. Let's break down. A polynomial of degree n can have up to n minus 1 turning turns. A cubic n3 can have 2 turns. Roots and other one. A polynomial can have still n minus 1 turn. A degree can have but only 3 times if the curve moves up and down like while still 6 times. Yeah. Degree 6 polynomial with 6 roots. The polynomial is it can have fewer than 5 because the curve does not need to change at every root. Imagine a 6-degree polynomial that crosses the x-axis 6 points. The function might only turn 3 times. Here's the plot of this degree polynomial head dot function interval. This train. हाँ ખબર નહીં હું તો બેસીશ પછી in this same example the non-sure is not sure how using to speak when anybody that I got it, but समझ नहीं आ रहा मेरे को इतना ज्यादा. Is it hallucinating? But we got to know we got to understand, but now have an understanding of slope. Yeah, with all this, we do know what is slope, right? The slope came one there because it is because we have added c only, and it will get increased only because now can I tell him? It seems like I can't do more embedded right now. Please target how I can describe what the graph would look like. We are easy data and analysis limit your data target tomorrow after each and declaration. It's okay, bro. You're done. You're done. Good job, man. It's it's just crazy. It is crazy, bro. Crazy. I got it, bro. The degree has a setup of meaning time plus it to 6 roots. Yeah, yeah. No worries. You have done enough. I got to know a lot about starting from derivative. So quadratic equations and their roots. Thank you. Just one small request. Can you summarize our conversation as a teacher and a student convo where you are the teacher and I am the student asking questions? Please summarize in a way that every important concept you use you taught is covered along with every important concept and real world analogy along with every important question that I have asked is also covered. It will take some time. With the time, yeah, let me just quadratic equations simplified.
Let's learn some vocabularies for quadratic functions. First, vertex. What is the vertex of a quadratic function?
Man, this guy's hair is like a parabola. Should I comment? No, yeah, it is. He
First,
has this parabola shaped hairstyle. Solving JW advanced question. Trigonometry visualized. Don't memorize, just visualize. Zuckerberg. 21 YouTube settings, set small channel. Okay. He's making us dumber. Central machine learning building LLM. Crazy चीजें है ये तो please. RLHF. Rectified linear. This is activation functions, no? Zuzuru done. This much only? Okay. What is the slope of function? What does it mean when someone talks about the strength and response? What is slope? The slope measures the sharpness or sorry steepness of a function. For straight lines, the rise over run. For curves, the slope changes at every point, and we use derivatives to calculate at specific point. Real world analogy. Imagine walking on a hill. How steep the hill is at any point. Strength of the slope is how slope is very still. Strength, yeah. Zero means it's flat. Yeah. Response means how this steepness change. Key questions answered. Why do we normalize the function by the change in x to find the exact rate of change at a specific point rather than over a large section? Does the slope of zero means no change even if it's like yes that when the function is flat? Oh yes. Oh, अच्छा बात करो. So what does this actually means is uh slope is actually here. This question is good, that why do we normalize the function by the change in x? Because let's first understand with this straight line. Okay, why we are dividing the change in y by change in x? Because eventually we have to find the change in slope with the increase per unit. No, no. Let me just rephrase it. Eventually, what we need to find is that we don't want that in 5 meters the change was about 10-meter height. Okay, we actually want the that in what is the change after 1 meter. That's why we are dividing that. You got to- Why? Okay. Exploring point. Why does a straight line have no peak? Both quadratic equations have turns. What are turns? Still no peak. Why? He has one peak. Cubic can have two, can up to two because the derivative. Throwing a ball from parabola, it peaks at shoots are projected and the path of ball is thrown into the bridge construction. Proper understanding hiding expert. What happens how the number related? Come on, critical points. Why do we dare to find derivatives give the slope at turning process? Three takeaways. Bro, but you are not please add all the real world analogies anal analogies you have used for uh for derivatives, slopes, and quadratic equations. Sidarattare, oh, Sidarattare, oh. Someone watching the stream or not? Video quality SD. Eh? I am noob at this, huh? Live. Zero views. Zero views. If I okay, let me just if I go into this YouTube channel
My name is
and I can Andrej Karapathy. Karpathy. So I just need to restart. Hi, Sere, oh, Sere, oh, Turu. Guys, it got ended, no? Or is it live? Is it live? Is it live or not? I'll just go here. Gen AI Beast is live, bro. Is live, bro. Live, freaking live. I'll just go here. Yeah, we are live. We are live. Okay, so ChatGPT must have completed. Whoa. Let me check. What is a slow teacher explanation? This for function is increasing, function is flat, function is decreasing. So this driving under tells how the steep at road suddenly changes it represent turning point. The derivative is like the speedometer, tells how it fills the water. Yeah. Quadratic and cubic equations, explanation. These are the points where what do you have? Yeah, schema. Whoa, yo. Does a slope of zero mean no change even if x is slightly increased? Yes, at that each point. But yeah, how does we reach to this level? वो तो बताओ. Uh, Quadratic equation, cubic equation. These are the points. Yo, don't do this chat GPT with me. Okay. It is done actually. We got to know a lot about quadratic equations. Sorry, first of all, we started off with derivatives and their obviously how this is also done. So we got to learn more about derivatives, slope, then uh, then why the values of why the we can obviously write it by our own. Yeah, what does this all mean? Okay. What is the slope of function? Explain in exact real world analogy. So nobody can explain why tenure response. Okay, now frame this like there's a question in mathematics which okay, what is the slope? So indirectly you're asking how many square increase, the answer is 4. Does my match correct understanding? I'm preventing. Explain this in example. Yes, but why the slope here was calculated using the here if you are maybe sequence of willing rule, give me more like this of the real world use cases. This is nice. Okay, understood, but now I want to know how to material derive for a function like a behavior. How does this form great question? Understanding for data of how is it derived? What why that a straight line does not have any peak? So that's how we went into derivatives in quadratic equations. Satara rattara, ujjaga rattara, rattara, rattara. I guess let's conclude this. I'll be, you know, restructuring this, formatting it and create a concise summary here. Okay. So, and then I'll share it with you guys. We got to know what is derivatives and all. So, and how quadratic equations and all of this are linked to finding roots and all of this. But yeah, we are actually using no need for I am not going to explain much here, but yeah, we can do this. For slope, I guess we have understood slope and derivatives. Yeah. Okay, I guess that's it. Just to wrap up, I'll reiterate to the real world analogy of how derivatives are useful in machine learning. This ChatGPT gave me was give me more analogies: machine learning, heart rate, physics, economics, medicine, environment. Yeah. So gradient descent. In training machine learning models, derivatives are used to minimize error by finding the slope of the loss function and adjusting model parameters accordingly. So we are finding the slope of the function. If it is increasing, if it is decreasing, or if it is staying flat, right? So if the error rate is increasing, then we have to uh, we have to let's say let's say mm, let's say we are increasing the input value by some very small margin, okay, and then taking the derivative of it and calculating the loss function and the slope of the function, slope of the loss, okay. So if the slope is increasing, it means the error is increasing, right? So this gives us the uh, similar thinking that if I'll just reduce the input by some margin, if I'll perform subtraction, then the slope will decrease. So that's how this model gets the slope function, the loss function gets calculated. Okay, so this is a good definition. I'll just paste in this. No, I have not pasted. What is derivative? Derivative is an, if I'll just frame it my frame it in my own definition, is that derivative is measuring change at a very small intervals, or that, not intervals also, but it is like how fine we can chop something down and then observe its characteristic. That is a derivative for me. Yeah, because for internal interval, it's like, it's, yeah, it will be framed as time only, but derivatives is like this only, that how fine, how, how finely we can drill down, okay, we can narrow down something, and in that space we are observing its characteristic. That is derivative for me. Okay, that's it, guys. I'll just reformat this, okay, and we'll be uh, coming back tomorrow. Okay, we'll be proceeding with this, where Mr. Andrej Karapathy has started implementing code in his and building up the values and all of that. Okay, we'll think that if we want to code alongside, or it is just conceptualized only, we'll think and go forward for that. Okay, so I guess that's it. We have done it today. The task was completed. Uh, okay. Bye, guys. Okay, I just need to, what I need to do is, this one was part 2, right? This one was part 2, but we can take this quadratic equations and all. Yeah, we can take this quadratic equation and all in here. How steep example? Yeah, we can, this is part 3 that we did today. Okay, so let me just go. I'll just confirm that what all these answers, I do have some knowledge about them. What does it mean when we ask what is the slope of function? Slope of function means like, it's like we are calculating that it is increasing, decreasing, or it is staying flat. What does it actually means when someone says strength of slope or response? So the strength of slope is means like, it is basically a comparison metric. Let's say if you have two functions, okay, and you want to compare at the same intervals, and if you want to compare this functions, then the slope of function at same values will give you the strength of their slope. Let's say if I have a small hill, okay, which is not very steep, okay, and I travel on 1 meter in that. Okay, it's not that much steep. It's like this in this manner. This is the small hill, and the another hill is like this. It is this much steep. Okay, so if I travel, if I move forward 1 meter in both of this, then in which way I do I have to um, do I have to burn more energy? Obviously, in this, why? Because the slope of this high is high. Okay, so this means that strength of the slope of this hill is larger, is more as compared to the strength of the slope of this small hill, right? Response of the slope is like the changing. Okay, uh, how much the slope is changing at every moment. Yeah, that is normalize rise over run. So rise over run, this is a technique for straight slope. Okay, for straight lines, it is simply, if I want to calculate, let's say there's a hill which is going exactly in a uniform direction, there are no curves and all, then it is very simple. Then it is very simple that how do I calculate the slope? How do I calculate the rate of rate at which the height is increasing? So like for every 1 meter, if the height is increasing by 1 meter, so the slope will be 1, right? Okay, yeah, you got it. No, I got it, bro. It is up to you. Now you take. Okay. Um, at 0 point the slope comes to 0. It means like that as the slope so at 0.67 the slope comes to be 0, means that at that point the slope is 0. The slope is, we have reached a peak or a depression, and at that particular point the slope becomes 0, means there is no increase or decrease in the value of function. So that particular input value does not affect the function values. Okay, that means if we increase by 0 point, then also the slope will be 0 only. If we increase 0.67 by 0.0001, the slope will be 0 only, close to 0 only. Why we need to normalize the function with increased? Because we, at the end of the point, we have to know the unit change. Okay, that is why we have to normalize it. Does slope means the rate at which the function will change? The slope, yeah, it is a decrease or increase or decrease in value, right? Okay, so all of this is covered. All of this is covered. We have got good understanding, not the 100% understanding, but we do got a good understanding of this. Okay, which is okay enough to proceed further. Okay, and also for the future, if there will be some concept related to this derivative or differential equations or any of that, we'll always search. You can always search for it. But why I'm not diving 100% deeper into this, because to be very honest, derivatives is it's an ocean of mathematics. Okay, there will be a ton of interlinked things. Okay, there will be now trigonometries, graphs, this quadratic equations, all of this, it is kind of a large tree that I have need to go, but I don't have that much time. I need to start learning about this. So that is why getting a good overview of what actually derivatives mean is a good start. Okay, is a good place to start, because many of you might be in a similar situation where I was not taught about this real world use cases of what does actually getting a derivative of something means in real world. I know the chain rule, I know the product rule. You can, if you give me the equation, I can solve it theoretically, but but I was not able to visualize it as I'm doing it now. Okay, and also I'm quite resonating with this definition of machine learn of derivatives in machine learning. It's just like uh, the derivatives is just to calculate the slope of the loss function. Okay, basis the input value. So that's it, guys. I guess we are good to go for sign off. In the, as I said, in the next part 4 we will be proceeding with this uh, coding part. Okay, chalo guys, bye guys, bye, सो जाओ guys, सो जाओ, मस्त, bye.